All right, so welcome to Math 349, Operations of Order. I have this as lecture 23, and what I want to start doing today is talking about gaps. So there's a lot of different things you can study gaps between. You can study gaps between integers, powers of integers, primes, binary expansions, so on and so on and so on. And the goal, of course, is eventually to get up to Zeckendorf expansions and studying the gaps between summands there. So we will start with some easy problems and use that to build up. As you're writing your chapter, by all means, feel free to use the stuff that we're doing in class as a huge part of the chapter that you're writing up. One of the nice things about lecturing over writing in a book is you can actually get a sense of what is the audience understanding, both from facial expressions as well as from people raising hands, asking questions, sending emails. You can't do that when you're writing a book. The book has to be entirely fixed. You can have different material available, and you can choose, is the available going to be directly available in the chapter proper, or is it going to be an appendix at the end of the chapter, or is it going to be links to references outside of the book that people can look at? But when you're writing something down, you have a fixed format. We are not yet at interactive textbooks yet with a virtual professor who's lecturing, although that may be coming in a few years. All right, so let's start off by studying the integers. I'm assuming everybody is familiar with the integers. There's actually a formula for the nth integer. Does anybody know the formula for the nth integer? Yes, f of n equals n, right? This is not a very difficult function. There's also a formula for the gap between adjacent integers. So what would the gap be between n and n plus 1? Yeah, just one. Right? This should not excite anybody, right? It is really not that hard to study gaps between integers. What about powers of integers? If I give you, the kth power, let's call that function fk of n, what would that be? N to the k. And then gaps between kth powers, what would that be? So that would be n plus 1 to the k minus n to the k. So we have an explicit formula in this case. Is it ever possible that two different adjacent kth powers could have the same gap as two other adjacent kth powers? So in the integers, what are the possible sets of gaps you've seen between adjacent integers? Only one. Between adjacent kth powers, we get to see different gaps. Is it ever possible that I could have two different pairs of adjacent kth powers that have the same gaps? Like 3 to the k and 4 to the k, and 1,000 to the k and 1,001 to the k. Is that possible? Okay, why not? Could gk of n equal gk of m if k is greater than 1 and n does not equal m? I said k greater than 1. I'm covering my ass. So we know for integers, you can't ever have two adjacent integers having a gap other than 1. So the gap distribution is always 1, 1, 1, 1, 1. Okay. Well, now if I'm looking at kth powers, let's start looking at kth powers. Let's gather some data. Always gather data. So whenever you're, so here's n, and here's n to the k. What do we want k to equal? 2, right? Good choice, right? 1, 2, 3, 4, 5. So 1, 4, 9, 16, 25. And then we'll have, G2 of n. Do we want to include 0? Yeah, 0 sometimes makes things interesting. So if we include 0, we're not going to have a gap between 0 and the number before, but between 1 and 0, what would the gap be? It would be 1. Between 4 and 1 would be 3. 4 and 9 would be 5. 9 and 16 would be 7. Yeah, it's looking like there's a really nice pattern here. Now, of course, we have an explicit formula. We know that G2 of n is n plus 1 squared minus n squared, which is 2n plus 1. So is it ever possible we could have two gaps between squares that are the same? So is it possible that there are two different squares, pairs of adjacent squares that have the same gap? Could we see a gap of 5 somewhere further down the line? Why not? Good, the gaps are strictly increasing. So no. G2 is strictly increasing. And how do you know that?
Not 2n minus 1.
It's 2n plus 1, because we have n plus 1 squared minus n. So it's n squared plus 2n plus 1 minus n squared. If we take n equals, we're doing the gap between the number and the number, I guess, before it. So how do I want to phrase things? I guess I'm doing the gap of n is the gap between the number after it and itself. So this is the gap between n plus 1 squared and n. So depending on how you adjust things, you can easily change it so it could be the gap between the number and the number before it. I'm doing the number and the number after it.
Wait, so 3 refers to the gap between 2 squared and what?
Yes. Right. Going from 1 to so I should probably shift all these by 1.
Yeah. Okay. Yeah.
Yes. 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 The way I've defined thing, I should shift everything by 1. And that's the nice thing about doing like this. There we go. And what would the gap be between 25 and 36? 11. Did you do the calculation or are you just using the pattern? Yeah, just use the pattern. And we know it's 2n plus 1. So if we do it like this, it's it's very nice. So how do you prove that G2 is strictly increasing? Well, the problem might be easy, right? How do you prove that G2 is strictly increasing? So we know the integers are strictly increasing. So if we put in a larger n, we make G2 larger. So one way is by observation. Does anybody know another way to show a function is increasing? I'm sorry? Could do limits, but you've taken some classes that give you some techniques to tell if a function is increasing. Derivative, right? Check the derivative. So what would be the derivative? So derivative is 2, which is greater than 0, so increasing. So this is the simplest way to show that it has to be increasing. Okay. What if I give you GK? So GK of n will be n plus 1 to the k minus n to the k greater than or equal to 2. And I'm doing it like this because I don't want to have negative signs. That's why I'm doing it n plus k, n plus 1 to the k minus n to the k, rather than n to the k minus n minus 1 to the k. So how would you show GK's increasing? So take the derivative. So let's consider, gk of x will be x plus 1 to the k minus x to the k. And so now I have a function which agrees with my original function whenever x is an integer, but it extends it. Why do I have to do this extension?
It seems the same for you.
Well, initially I've defined my function gk on the integers. I'm now extending this to be a function of real values x. Why am I doing this extension?
So that we can have different gaps besides just one.
Not so we can have different gaps, because we're looking at kth powers. Why do I need to look at gk of x rather than gk of n? I'm trying to show it's increasing. What technique am I going to use? Has to be continuous. So what am I trying to do? I'm going to try to differentiate. So if I want to differentiate, I need to have a real variable to differentiate. If I have a function just defined at the integers, I can't use calculus. I can't do a limit argument. So what I can do is I can take this function, which agrees with the original function whenever the input x is an integer n, but it's defined for all values of x. And I can study this as a function of a real variable and then specialize to integers and get information out about the integers. This is a great way to use analysis in a variety of problems. So I want calculus to be available. I need to have a continuous differentiable function. So we extend to x and r to use calculus. So what would g prime of k be? So it's just going to be k x plus 1 to the k minus 1 minus kx to the k minus 1. So this is going to be k x plus 1 to the k minus 1 minus x to the k minus 1. What can you tell me about this? Always positive, right? Always positive. So no repeated gaps. So when we look at the kth powers, we're never going to see the same gap twice. Okay? So is everybody comfortable with gaps between integers and between powers of integers? These are boring. We need to make things a little bit more exciting. All right? Let's study all powers of integers. So what's the first number that's the power of something? 0 or 1. And after 1, what's the next one? So if we consider powers of integers, is 5 a power of an integer? Is 13? Is 12? So if we do powers of integers, what's the set of powers of integers? So we need to be a little bit specific about powers. And we want the power at least 2. Because if we just study all powers of integers, it's going to be boring. It's just studying the integers again. So we'll only consider squares, cubes, 4th powers, 5th powers. We'll consider all of them together. So what's the next number after 1 that's a square, cube, etc.? 4. And after 4. And after 8. And after 9. 16. Then what? 25. After 25. 27, not 36. And so now let's start looking at the gaps. We have 1. I'm sorry? Got 32. Thank you. So we'll have 32, 36. And so we have 1, we have 3, we have 4, we have 1 again, we have 7, 9, we have 2, we have 5, we have 4 again. All of a sudden, the problem has become a lot more interesting. We could look at maybe just powers of 2 and powers of 3. Well, I'm looking at powers of all numbers. So do we agree that this is far more interesting than just looking at integers or just fixing a power? Did I make a mistake?
No, I'm just curious what to do to get the numbers in.
We're looking at powers of integers with the powers at least 2. So we're looking at squares, cubes, fourth powers, etc.
Oh, for every-
Yep. So we're looking at all squares, cubes, fourth powers, ... all of these. And we're looking at what are the possible gaps when we look at something like this. And so we see 1 is a gap, we see 2 is a gap, we see 3 is a gap, we see 4 is a gap, 5 is a gap, 7 is a gap. So we can have a little table. Observed gap and the number of occurrences. We have 1, 2, 3, 4, 5, 7. And 1 has occurred twice, 2 has occurred once, 3 has occurred once, 4 has occurred twice, 5 has occurred once, 7 has occurred once. Oh, and we have a 9 as well. We can squeeze that in. So what would you conjecture? Oh, sorry. Yes. So what would you conjecture? So in what way? So that's an interesting question. Now, as we go further down, more gaps are going to become available. So absolutely could ask Ben for this. What else could we ask? You know, look at the data. Most frequent. And that could change depending on where we go. So there's something called prime number races to see which gap between primes occurs the most often. And initially, 2 and 4 basically tied, then 6 takes over, then 30 takes over. So anybody notice anything interesting about the numbers 2, 6, and 30? The next one is 210. So going from 2 to 6, 6 to 30, 30 to 210. Yeah, so these are called the primorials. The primorial is the product of all the primes up to. So the first primorial is 2, then the next is 3, then the next is 30. You just multiply by the first k primes. And it turns out that we believe each primorial is the champion for a while and then is overthrown by the next primorial. I don't remember exactly where the state of the art in proofs of results like this. But you will have a winner up to a certain period of time, and then that winner will fade and a new champion will emerge. This sounds like a really bad movie. But it makes sense because we'll see later that the gaps between primes are growing. So the average spacing between primes is getting larger and larger and larger. What else could you guess or conjecture from this? So we see gaps of length 1, 2, 3, 4, 5, 7, and 9. So they're going to get larger. So that's a question. So that's a good question. Do we get arbitrarily large gaps? So is 4 the last even? I assume nobody is comfortable making conjectures based on small data like this. right? We do not have anywhere near enough to make a conjecture. I doesn't want to let me paste today. All right. So, gap, and then number of times. So the gaps we had was, we had 1, 2, 3, 4, 5, 7, 9. And one occurred twice. What was the other one that occurred twice? Was it 4? And everything else was a 1, right? So what are the conjectures? 1, 5. What else might you conjecture? So we talked about, as we go far down, do we expect to see arbitrarily large gaps between numbers? We're now talking about all these powers coming in. So it might be hard to get very large gaps. If we look at, say, just cubes, we know that the average spacing between cubes is going off to infinity. But if we look at all possible powers, maybe something can always sneak in between things, so we're not going to have a large gap. So, are the gaps bounded? Well, what about on the other end? So that was talking about extreme gaps. You want to learn how to make conjectures. What's the opposite of large gaps? Small gaps. So what might you conjecture about small gaps? So give me a conjecture about gaps of length 1. So many gaps of length 1? Is that a reasonable conjecture? Are you confident on that conjecture?
Do we count gap length 0?
Well, we're not going to have gaps of length 0, because that would mean that the numbers would be the same.
I was thinking the case that like 2 to the something equals 4 to something.
Right. It's still the same number, and it could be on the list for multiple reasons. So you could be on the list as both a square and a cube, and a 4th power. That's fine. But we only count you as a number on the list once, and so when we're looking at the gaps, we're looking at gaps between adjacent numbers. So there's actually a theorem. It's the Catalan conjecture. Only gaps of length 1 are 0, 1, and 8, 9. So that's actually a theorem due to Milesker. So you will never see any other gaps of length 1. So the theorem, you could also interpret it as, there's a bounded number of gaps of length 1. It is a bound of 2. There is one more possible gap that maybe if you use negative numbers, we'll just use positive numbers. Knowing that, what might you conjecture about gaps of length 2? Maybe bounded number of gaps of size G. And then you could even try to maybe conjecture maybe how many such gaps are there. So again, a lot of math is trying to figure out what to ask. Part of this could be in terms of just creating problems for a book, or research problems for people to look at. And here, all of a sudden, just by looking at a couple of things, there's one other natural question to ask based on the data that I've given you. Yes?
I was going to ask, when we think about problems with the books, would you recommend trying solutions to all of them?
If you're able to do solutions to all of them, that's great. That's more time consuming. Sometimes, if you want to have like hints that can be either made available or not available. But there's one more really natural looking at the set of gaps is 1, 2, 3, 4, 5, 7, 9. I think it's related to your do is for the last even. So it's very similar to is for the last even. So is every number, or which numbers are gaps? No. From earlier, maybe 4 is the last even number, so we're not going to have any 6s, 8s, 10s, and so on. But is every odd number going to be a gap at some point? So you could start trying to gather some data for something like this. And again, if you're trying to write a chapter on gaps, here is some problems that should be related to things people have seen before that they can experiment with, and hopefully they don't know the answer to begin with. The fact that there's only 2 pairs that have a gap of length 1, this was a major result that was only proved, I'd say, in the last 20, I'll say 30 years to be safe, because I think it might have been around 20 years ago. It might have been around 2002. I don't remember. But again, I want you to get to the point where you are gathering data, and I want you to get to the point where you're trying to come up with what would be good problems to study. Okay, any other questions on gaps between powers? You could always make the problem a little bit easier or maybe a little bit harder by restricting to, I'm only going to look at powers of 2 and 3, or powers of multiples of 2 and 3. Oh, I'm sorry, powers of numbers whose only factors are 2 and 3. Okay. So let's continue to get more complicated things to study. Let's look at prime numbers. Can somebody give me a definition of a prime number? No. So the definition of a number is prime if it's only divisible by 1 in itself is wrong. It's close, but it's wrong. Nope. You're really close. What's the first number that's only divisible by 1 in itself? 1. So your definition would allow 1 to be a prime. So one thing you could say is these are integers greater than 1 whose only factors are 1 in itself. We could say positive integers with exactly 2 factors, 1 and itself. So that would work. And so we consider 1 a unit, and then if n equals a times b with a, b greater than 1, we say n is composite. You could say with exactly 2 distinct factors. Yep. So we'll put in distinct just to be safe. So we don't want 1 to be a prime. And the reason we want 1 to be a unit, so we have the following theorem. This is the fundamental theorem of arithmetic. Any n can be written uniquely as a product of primes in non-decreasing order. So for example, if I give you 144, that's 4, 12 is 4 times 3, so it's going to be 2 to the 4th times 3 squared. So it's 2 times 2 times 2 times 2 times 3 times 3. I can commute the order of the 2's and the 3's, But I'm always going to have exactly 4 2s. I'm always going to have exactly 2 3s. And so we have a fixed way of writing numbers like this so that we have a uniqueness. I'm going to write all the powers of 2 first, and then all the powers of 3, then all the powers of 5, then all the powers of 7. If I do that, there's a unique way of writing it. If I don't say that I have to write them in a non-decreasing order, I could factor 144 as 2 times 2 times 3, 2 times 2 times 3. I don't want to consider that as a separate factorization. How many of you have seen the fundamental theme of arithmetic? You don't get the name fundamental lightly in mathematics. So whenever you have a fundamental, something important is going on. So the primes are the building blocks of integers. So every integer can be written uniquely as a product. I'm not going to go through and prove lots of things about primes, but we can start asking questions about gaps between primes. So let's study gaps between primes. So what's the first thing we should do to study gaps between primes? Start with some data. So we have 2, 3, 5, 7, 11, 13, 17, 19, 23, 27, dot, dot, dot. Oh, not 27, 29. And so we start looking at the gaps. We've got 1, 2, 2, 4, 2, 6, 2, 6, 6. With small amounts of data, things can be very misleading. When you look at this, what are some things you might conjecture? Okay, you can do better than that. Good conjecture. All but first gap are odd. Every other prime after 2 is going to be odd, so all the gaps will be even except for the first one. Oh, sorry, all but first gap are even. First gap is odd. I'm sorry?
13 to 17.
Oh, 13 to 17 is 4, sorry. Sorry, thank you. So that should be 4. That should be 4. Excellent. 4, 2, 4, 2. Okay, good. So it goes 2, 4, 2, 4, 2, 4. If you just look at that for a while, you might think it's always alternating 2, 4, 2, 4, 2, 4, but then we get the 6. So when you look at this, we're seeing a lot of 2s, a lot of 4s. If we didn't do the 23 to 29, we wouldn't see the 6 at all. And maybe we think maybe everything is just going to alternate 2, 4, 2, 4. So again, your conjectures could be wrong, but when you look at this, what might you conjecture? Sure. Maybe cycles. So maybe cycles, 6 is the largest. Maybe 2 and 4 are the most frequent. Maybe have 2, 4 infinitely often. And maybe gaps get arbitrarily large. So sometimes the first thing we try to do is prove something happens, in existence. Then we sometimes try to either be constructive and show a way to actually realize it, or we try to quantify how often can that happen. So we want to try to show some of these statements. It's still open whether or not there are infinitely many gaps of length 2 or 4. So having infinitely many gaps of length 2 is known as the twin prime conjecture. Since I came to Williams, there have been remarkable advances. And so for the longest time, there were only weak results about how many gaps can you have of a fixed length. And then, in the past, 15 years, there was a remarkable breakthrough by Yiteng Zheng, who showed that there were infinitely many pairs of adjacent primes whose difference was at most 70 million. Now, this was a remarkable result. No one had ever been able to show that there were infinitely many primes whose gap to the next prime was bounded by a fixed number. So when he wrote up his paper, he deliberately did not try to come up with the best bound possible. He was going for what is the easiest argument I can give, the easiest that will be for people to look at and make sure that it's correct, to show that there is a bounded gap that occurs infinitely often. And then you can open up the floodgates and try to make that bound as small as possible. And people have gotten it to be smaller and smaller and smaller, but there are fundamental obstructions to the method to go all the way down to 2. But they've been able to get it much, much smaller. This is not a number theory class, so I'm not going to detour too much into that. I will resist the temptation. But there's remarkable stuff that's been proven. So what I will do right now is I will show that there are arbitrarily large gaps between primes. Of course, before I do that, if I want to show that there's arbitrarily large gaps between primes, what do I need to know about the primes? So the actual value, or that they're infinitely many. If there are not infinitely many primes, this is going to be a very boring subject. So there are infinitely many primes. And one of the earliest proofs goes all the way back to Euclid. The copyright has long expired. This proof is over 2,000 years old. It's a really nice proof by contradiction. Assume not. So P1, P2, ... Pn are all the primes. Consider x equals P1 times P2 times Pn plus 1. What are the possibilities for x? X could be, what kind of number could x be? It could be prime. And what's the other possibility? Composite. Well, if x is prime, contradiction. X is larger than Pn, not in list, and we assumed list was complete. So if x is a prime number, it should have been on our list, and we assumed we wrote down all the prime numbers. So x must be composite. So we can write x as a product of 2 numbers. So I can write x as a prime times something at least 2, right? So if you're not a prime, you have to be divisible by a prime. And just for definition, this is 2 times 3 times 5 times 7 times Pn plus 1. Can 2 divide x? No, why not? 2 does not divide x as remainder is 1. Can 3 divide x? No, why not? And all the way to Pn cannot divide x as remainder is 1. So prime not on list divides x. Yes?
Is this the same thing about primordial?
So x is essentially one more than a primordial.
Oh, that's like a P and then plus 1 separately.
Yes, yes. So it's all these numbers plus 1. So we multiply all the primes together and add 1. So this is really the nth primordial. So the primorials are wonderful numbers. They have tremendous properties. And from this, we can actually deduce that either x is a prime, which is great, or it's divisible by a prime not on our list. So either way, the list was incomplete, so there has to be another prime. With a little bit of work, you can actually use this to get a really bad estimate for how many primes there are at most x. I'm not going to go into that now. What I want to do now is I want to show gaps. So theorem. Gaps between primes can be arbitrarily large. So proof one, this is the elephant gun or the atomic bomb. You prove the prime number theorem. So pi of x is defined to be the number of primes p less than or equal to x. And you show that pi of x is approximately x over log x. So we have basically x over log x primes from, say, 0 to x. We have x numbers. So average gap is about by interval length x divided by the number of items, which is log x, which goes to infinity. So if I have 15 items going from 0 to 100, then roughly the average spacing has to be 100 divided by 15. If I had 25 items, the average spacing would be roughly 100 divided by 25, or 4. The more items I have, the smaller the average gap is. The fewer items I have, the larger. And again, you've got to be careful. Maybe I should add one or subtract one down below because I'm not having a prime at the very end of my number. I don't care about that. So if I can prove something big like the prime number theorem, about how many primes there are not enough primes to have a small average gap. So if the average gap is of size log x, then the average gap has to get very large, which means a lot of the time we have to have large gaps between numbers. So let me give you a second proof, which is more constructive. And it allows me to introduce some new notation. So we've been talking about primorials. So the kth primorial is written as pk sharp. So that's p1, p2, ... pk. So p1 is 2. I'm sorry, p1 primorial is 2. p2 primorial would be 2 times 3, which is 6. p3 primorial would be 2 times 3 times 5 is 30. Okay? So let's consider the number pn primorial plus, let me think. Plus 2. Let's see, go into plus 2. No. Let's do plus 1. Okay. Could this number be prime? Well, let's think. If we take p2 primorial and add 1, we would get 7. Yeah, if we take p3 primorial and add 1, we would get 31. If we take p1 primorial and add 1, we get 3. Maybe it's always prime? How many of you watched the video I sent? So this is where patterns can fool you. So we might talk more about this tomorrow. So is it possible that this is prime? It's possible that this is prime. So we have Pn primorial plus 1. So this is maybe prime. Okay. Now, let's look at Pn primorial plus 2. Could that be prime? Why not? Composite. It's a multiple of 2. All right. What about Pn primorial plus 3? What about that? So could that be prime? This has to be multiple of 3, so it's composite. Multiple of 3. No, it's P1 times P2 times P3 times P4.
You just take the P1 times the P1 primordial.
So here n is big. Okay, so here where n is big. So 3 is going to be less than n. What about the next one? Pn primordial plus 4. So it's composite. So it's a multiple of 2. And we can keep marching down. And I claim, even when we get to Pn primordial plus Pn, what's this a multiple of? Multiple of what? Not n. I'm sorry? P sub n. So I claim that all of these numbers are composite. So the next number that could possibly prime is one more than all of this. So if I look at Pn primordial plus Pn plus 1, maybe it's prime. Okay. So if I look, this might be prime, this might be prime. We have here a stretch of composites. And what's the length of those composites? So if I go from 1 to 5, how far is it from 1 to 5? 4. So I'm going from Pn primordial plus 2 to Pn primordial plus Pn, and then one more over there. So it's basically going to be of size, Pn maybe plus 1, something like that. Does everyone agree it's approximately Pn?
Yeah.
So I've just shown you that I can physically construct a gap between prime numbers. Maybe this isn't prime. Maybe I have to go a little bit further to the left. Maybe this isn't prime. Maybe I have to go at least a little bit further to the right. I've shown that there's a gap of length at least Pn plus 1 between primes. So the gaps between primes have to get arbitrarily large. This is a constructive proof. I've even told you where to look. And I'm guaranteeing that you will see a gap of at least a certain size. This is also extreme overkill. This is yes, there's going to be a gap this large, but this is going to be so much smaller than the average spacing between primes that it's not even close. It's absurd to use this. You've gone so far down, the average gap might be the exponential of this. That's fine. It's enough to prove that there is a gap of a given length. So now what we're going to do on Wednesday is we will start trying to study gaps between binary expansions and then Zeckendorf expansions and try to talk about what can we say about gaps there. But I wanted to just start off with some general questions and just see how easy it is to get to things that we don't know. If people are interested in prime numbers, let me know. And there's a little bit more I can say about some of the patterns in prime gaps and some of the patterns in Euclid's theorem of proving that they're infinitely many. So it looks like these primorials plus 1 are always prime? And there's some interesting questions you can ask about that as well. All right, have a good day.